Mars has long captured the imagination of humanity. A distant world that shines like a burning ember in the night sky, close enough to see, yet far enough to remain mysterious. For centuries, it has been the planet of legends and questions, a place where ancient astronomers imagined canals and civilizations, and modern scientists search for traces of life. It is both familiar and alien, a smaller cousin of Earth with mountains taller than Everest, canyons deeper than any on our planet, and deserts that stretch farther than the eye can see. Its thin air, freezing winds, and rusty soil tell a story written in stone and dust. A story of a world that may once have flowed with rivers and lakes, where conditions could have allowed life to take hold. To study Mars is to look into a mirror of what Earth might have been in its early days, and perhaps what it could become. Every rover that crawls across its surface and every orbiter that circles above brings us closer to understanding this enigmatic neighbor. A world that challenges our knowledge, stirs our curiosity, and beckons us ever onward across the void. One of the most striking similarities between Mars and Earth is the length of their days. A Martian day, known as a sol, lasts about 24 hours and 39 minutes, only 39 minutes longer than a day on Earth. In the vast diversity of the solar system, where days can stretch into weeks or even years, this closeness is remarkable. It means that the rhythm of day and night on Mars is almost identical to the one life on Earth has evolved around. Despite the stark differences between the two planets, in size, atmosphere, temperature, and environment, their shared daily cycle creates an unexpected bond. This similarity in day length is a result of how Mars spins on its axis. Like Earth, Mars rotates once roughly every 24 hours, turning from day to night and back again as it orbits the Sun. That rotation speed shapes much of the planet's character. It affects its weather, the patterns of light and shadow across its surface, and the way temperatures rise and fall. On Mars, as on Earth, the day begins with the faint glow of dawn spreading across the landscape. The sun climbs higher, warming the dusty plains and rocky craters, before dipping below the horizon again, leaving the planet bathed in the chill of night. For a visitor from Earth, this cycle would feel familiar. The slow turning of the sky, the regular return of daylight, the nightly descent into darkness. Because a sol is so close to an Earth day, it has practical importance for exploration. When robotic missions land on Mars, their schedules are often planned according to Martian time. Engineers and scientists working with rovers like Spirit, Opportunity, Curiosity, and Perseverance have sometimes adjusted their own daily routines to match Mars' rhythm, shifting their workdays slightly forward by about 39 minutes each day. Living on Mars time means starting work later each day, but it keeps mission teams aligned with the daylight hours on the Martian surface, which is crucial for solar-powered equipment and communication windows. If a Martian day were drastically shorter or longer, synchronizing missions would be far more complex. The length of a Martian day also influences the planet's climate and atmosphere. Because the day is close in length to Earth's, Mars experiences similar patterns of daily heating and cooling, though more extreme due to its thin atmosphere and greater distance from the Sun. During daylight, the surface can warm significantly under the weak sunlight, but as night falls, heat escapes quickly into space, plunging temperatures well below freezing. Dust storms, wind patterns, and even frost formation follow this daily rhythm, shaped by the steady alternation of sunlight and darkness. For future human explorers, the near match in day length is more than a curiosity. It is a real advantage. The human body's internal clock, or circadian rhythm, is naturally tuned to a roughly 24-hour cycle. Adapting to the days on Mars would likely be far easier than on worlds where a day lasts much longer or shorter. On Venus, for example, a single day is longer than its year, and on Jupiter it lasts less than 10 hours. Such extremes would challenge human physiology and psychology. Mars, by contrast, offers a daily rhythm close to what humans evolved with, making it a more hospitable destination in this respect. The fact that a Martian day is almost the same length as Earth's is a quiet but powerful reminder that our worlds share more than just a place in the same solar system. Amid all their differences, in atmosphere, gravity, and habitability, this shared rhythm of sunrise and sunset links them. It means that on Mars, time flows in a way we understand. The planet spins to a beat that feels familiar, turning beneath the same sun that lights our own skies. And in that shared motion, Mars becomes not just an alien world, but one that echoes the daily life of home. Mars takes its time to journey around the sun, while Earth completes its orbit in about 365 days. Mars needs 687 Earth days to make a full circuit. A Martian year is therefore nearly twice as long as ours, a difference that shapes almost every aspect of life and environment on the red planet. This slower pace is not a matter of chance but of distance. Mars lies farther from the Sun, about 228 million kilometers away compared to Earth's 150 million. The greater distance means a larger orbit and a weaker pull from the Sun, so Mars moves more slowly along its path. That leisurely pace stretches its seasons and defines its unique rhythm of time. The length of a Martian year has profound effects on the planet's climate and seasons. Like Earth, Mars is tilted on its axis, about 25 degrees compared to Earth's 23.5, which gives it 4 seasons: spring, summer, autumn, and winter. But because Mars' orbit takes nearly twice as long, each season lasts roughly twice as long too. A Martian spring, for example, can last around 190 Earth days, while winter can stretch to about 150. These extended seasons shape the behavior of the planet's thin atmosphere and surface conditions. When spring arrives in the polar regions, vast caps of carbon dioxide ice slowly sublimate into gas over many weeks, swelling the atmosphere. In winter, the reverse happens as carbon dioxide freezes out of the air and deposits on the surface, shrinking the atmosphere again. These long, slow cycles create patterns of wind, pressure, and temperature that differ greatly from Earth's more rapid seasonal changes. For any future human explorers or settlers, the length of a Martian year would deeply influence life and planning. A single year there would represent nearly 2 Earth years, meaning that calendars and schedules would need to be reimagined. Agriculture would follow a slower rhythm, with planting and harvest tied to seasons that last for months longer than we are used to. Even marking the passage of time would feel different. Birthdays, anniversaries, and mission milestones might occur less frequently when measured in Martian years. Scientists studying long-term weather patterns or geological processes would have to think in terms of longer seasonal cycles. The longer year also affects how Mars interacts with Earth. Because the two planets travel at different speeds around the Sun, launch windows for missions, the times when Earth and Mars are close enough for spacecraft to travel efficiently, occur about every 26 months. This means opportunities to send probes or people are relatively rare, shaped by the rhythm of Mars' orbit. Understanding and working with that timing is crucial for space agencies planning exploration. The extended Martian year influences more than just science and logistics. It also shapes how we imagine life there. Days on Mars feel familiar, just 39 minutes longer than on Earth, but the passage of years would feel almost stretched. Children born on Mars would celebrate birthdays half as often if measured in Martian years. A person living there for 20 Earth years would be only about 10 Martian years old. This change in how time is marked reflects the deeper truth that time itself flows differently on another world, defined by its motion around the sun. Mars' long year reminds us of the vastness of the solar system and the delicate balance of orbital mechanics. A planet's distance from the sun is not just a number. It shapes its climate, its seasons, its exploration, and even the way time is experienced. On Mars, the slower pace of a nearly 687-day year is part of its identity. A cosmic heartbeat that ticks more slowly than Earth's, but just as steadily. It is a rhythm that speaks of a world farther out in the solar system, turning patiently under the same sun, living life on a longer, wider scale. Mars, the small and rust-colored planet that glows faintly red in our night sky, is accompanied on its lonely orbit around the sun by two tiny companions, Phobos and Deimos. Unlike Earth's single, stately moon that shines with a steady and commanding presence, the Martian moons are irregular, shadowy bodies, more akin to drifting rocks than grand celestial spheres. They are small enough to appear as mere points of light to an observer standing on Mars's surface, but their presence adds a strange intimacy to the planet's austere beauty, a quiet reminder that even a barren world can have company. Phobos, the larger of the two, is a battered world scarcely 22 kilometers across at its widest point. Its surface is gouged by craters and streaked by long grooves, the scars of countless impacts over millions of years. To a Martian observer, it would appear to race across the sky, rising in the west and setting in the east, a reversal of Earth's familiar pattern. Phobos orbits so close to Mars, only about 6,000 kilometers above the surface, that it circles the planet in just 7.5 hours. Because it moves faster than Mars rotates, it appears to speed overhead 3 times in a single Martian day. As it does, its rugged silhouette casts fleeting shadows over the desert plains, a restless companion tethered tightly by gravity, doomed to spiral ever closer until one day, perhaps tens of millions of years from now, it will shatter or crash into Mars itself. Deimos, on the other hand, is the gentler sibling, smaller, smoother, and more distant. Barely 12 kilometers across, it looks more like a drifting asteroid than a true moon. Its orbit, about 23,000 kilometers away from Mars, allows it to move more slowly, rising gracefully in the east and setting in the west, much like our own moon but in miniature. To someone standing on the Martian surface, Deimos would appear as a bright, swift-moving star, barely large enough to cast a shadow. It completes its orbit every 30 hours, never in a hurry, always keeping its delicate distance. If Phobos is the restless heart of Mars's sky, Deimos is its quiet watcher. The origin of these moons has long fascinated astronomers. Their irregular shapes and dark surfaces resemble the carbon-rich asteroids that inhabit the outer regions of our solar system. Many scientists believe that both Phobos and Deimos were once wandering asteroids, captured by Mars's gravity in some ancient encounter. Others suggest that they may be the remnants of a larger moon, shattered by a cataclysmic impact that sent fragments into orbit, which later coalesced into the 2 small bodies we see today. Whatever their beginnings, they have become integral to Mars's identity, relics of the chaotic past that shaped the planet's fate. From a scientific perspective, these moons offer more than poetic companionship. They are laboratories in miniature, their surfaces coated with fine dust and debris that preserve the history of the solar system. Future missions aim to land on Phobos and Deimos, to study their composition and perhaps even bring samples back to Earth. Understanding their makeup could reveal whether they are indeed captured asteroids or formed from Martian material. An answer that would illuminate not only Mars's past, but the violent processes that governed the early solar system. And yet, beyond the science, there is something quietly haunting about these two moons. They are the planet's constant witnesses, tracing endless loops through the Martian sky while the world below changes only in the slowest of ways. Phobos, doomed to fall, and Deimos, destined to drift farther away. Together they enact a celestial dance of approach and retreat, closeness and solitude. In their motions, one might see a reflection of Mars itself. A world once vibrant and alive, now caught between memory and silence, holding fast to its two fragile companions as it circles the sun in eternal solitude. Mars may look like a world not so different from Earth at first glance, with mountains, valleys, polar ice caps, and clouds drifting across its sky. But one crucial difference shapes everything about it. Its atmosphere is extremely thin. The blanket of gas surrounding Mars is less than 1% as dense as Earth's, meaning that standing on the surface of Mars would feel like being almost 35 kilometers above Earth's surface, far higher than any airplane can fly. This thin veil of air profoundly influences the planet's weather, temperature, surface conditions, and potential to support life, past or future. The main reason Mars has such a thin atmosphere lies in its size and history. Because Mars is about half the size of Earth, it has weaker gravity, only about 38% of what we experience here. That lower gravity makes it harder for the planet to hold on to light gases like water vapor and nitrogen. Billions of years ago, Mars likely had a thicker atmosphere and flowing water on its surface, but over time much of that atmosphere was stripped away. As Mars cooled, it lost its magnetic field, which had once shielded it from the solar wind, the stream of charged particles flowing from the sun. Without this magnetic protection, the solar wind gradually eroded Mars' atmosphere, sending much of it into space and leaving behind the thin layer that remains today. The composition of Mars' atmosphere also reflects this transformation. It is about 95% carbon dioxide, with small amounts of nitrogen, argon, and trace gases like oxygen and water vapor. While carbon dioxide is a greenhouse gas on Earth, the Martian atmosphere is too thin to trap much heat. As a result, Mars cannot retain warmth effectively, and surface temperatures swing wildly from day to night. In the daytime, sunlight can warm the ground to near 20 degrees Celsius in some regions, but at night temperatures often plunge below -70 degrees Celsius. These extreme variations create a challenging environment for any potential life and for future human explorers. The thin atmosphere also means that Mars has almost no surface pressure. On Earth, the air around us presses down with about 1,013 millibars of pressure at sea level, but on Mars it averages only about 6 to 7 millibars. That is so low that liquid water cannot exist on the surface for long. It either freezes or evaporates almost instantly. The lack of pressure also affects weather patterns. Clouds do form in the Martian sky, mostly from carbon dioxide or water ice crystals, but they are thin and wispy. Winds can still sweep across the landscape, lifting fine dust and creating massive dust storms. But these winds feel far gentler than their earthly counterparts because the air is so light. For future explorers, the thin atmosphere poses both challenges and opportunities. It offers almost no protection from harmful solar and cosmic radiation, meaning that humans on Mars would need to live in shielded habitats or underground structures. It also makes traditional aviation difficult, since there is not enough air to generate lift for aircraft designed for Earth. On the other hand, the carbon dioxide-rich air could be used to produce oxygen through chemical processes, and understanding how to work with the thin atmosphere will be key to building a sustainable presence on the planet. The thinness of Mars' atmosphere also tells a story about time and change. It is a remnant of a world that was once more active, with rivers, lakes, and perhaps even a thicker, warmer climate. Today, that past is written in dry riverbeds and sedimentary rocks, while the sky above remains almost airless and silent. Mars' extremely thin atmosphere makes it a harsh, cold, and exposed world. But it is also a world that invites us to study how planets evolve and how fragile their environments can be. Beneath that tenuous sky, the red planet continues its slow orbit around the sun, a world stripped nearly bare, yet still full of secrets waiting to be uncovered. Among the many remarkable features of Mars, none is more awe-inspiring than Olympus Mons, the tallest volcano in the entire solar system, rising about 22 kilometers above the Martian surface, nearly 3 times the height of Mount Everest. This immense shield volcano is so vast that it stretches roughly 600 kilometers across, about the size of the entire state of Arizona. Its slopes are gentle, averaging only a few degrees, yet they rise steadily to a summit caldera 80 kilometers wide. Olympus Mons is not just a mountain. It is a colossal geological monument that tells the story of Mars' volcanic past and the forces that have shaped its surface. The sheer size of Olympus Mons is possible because of Mars' unique conditions. The planet's gravity is only about 38% as strong as Earth's, which allows structures to grow taller before their weight causes them to collapse. This weaker gravity, combined with the planet's lack of plate tectonics, gave Olympus Mons the time and stability to grow over hundreds of millions of years. On Earth, volcanic hotspots like those beneath Hawaii are constantly moving relative to the tectonic plates, so new volcanoes form while older ones become dormant. Mars, however, has a rigid crust that does not shift in the same way. The same hotspot remained beneath one location for eons, allowing lava to pile up layer upon layer until Olympus Mons became the towering giant we see today. The volcano's immense size also reflects the nature of Martian lava. It is very fluid compared to the thicker lava found in many Earth volcanoes, so it spreads easily over great distances before cooling and hardening. Over countless eruptions, this created the wide, gently sloping shield shape characteristic of Olympus Mons. Each eruption added more material, expanding the volcano's bulk outward and upward until it reached its extraordinary dimensions. Because erosion is slower on Mars, with no rain and little wind compared to Earth, Olympus Mons has remained relatively unchanged for millions of years, preserving its massive form. Olympus Mons is more than just a geological wonder. It offers clues about Mars' history. Scientists believe it was most active between 200 million and 2 billion years ago, a relatively recent period in planetary terms. Some evidence even suggests that volcanic activity on Mars might not be entirely extinct. If Olympus Mons or other volcanoes were to erupt again, they could reshape parts of the Martian surface and release gases into the atmosphere, potentially influencing the planet's climate. Studying Olympus Mons helps scientists understand how Mars cooled over time and how volcanic processes differ on planets without plate tectonics. For future explorers, Olympus Mons stands as both a challenge and an opportunity. Its vast slopes and towering summit could provide valuable vantage points for studying the Martian surface and atmosphere. The volcano's volcanic rocks might reveal details about the planet's interior and its geologic evolution. Even the ancient lava tubes that likely lie beneath its surface could serve as potential shelters for astronauts, protecting them from radiation and extreme temperatures. The existence of Olympus Mons also reminds us of the dramatic differences between Earth and Mars. On our planet, gravity, weather, and moving tectonic plates limit how large a volcano can grow. On Mars, the combination of lower gravity, A stable crust and slow erosion allowed nature to build something on a truly colossal scale. It is a monument to the power of volcanic activity and the quiet persistence of geological time. Olympus Mons is more than just the tallest volcano in the solar system. It is a symbol of Mars itself, a planet shaped by forces both familiar and alien, a world where familiar geological processes unfold on a scale that defies earthly comparison. Towering into the thin Martian sky, it stands as a silent witness to the planet's fiery past and a striking reminder of the extraordinary landscapes that await us beyond our own world. Beneath the silent, rust-colored surface of Mars, the planet is not as still as it seems. Though it lacks the shifting tectonic plates that constantly reshape Earth, Mars trembles from time to time with its own subtle quakes. Marsquakes, as scientists have named them. These faint shudders ripple through the crust, whispering of the restless forces that still dwell deep below. They are the echoes of a planet that, while ancient and quiet, is not entirely dead. Marsquakes reveal that the planet's interior still moves, flexes, and cools, continuing a slow and secret evolution that began billions of years ago. The first real evidence of Marsquakes came in 2018, when NASA's InSight lander touched down on the flat expanse of Elysium Planitia. Designed as a stationary geophysical observatory, InSight carried a sensitive seismometer, an instrument capable of detecting the faintest vibrations from within the planet. For the first time in history, Mars had an ear pressed to its surface. What it heard over the next few years changed our understanding of the red world. The lander recorded hundreds of quakes, some little more than murmurs, others sharp enough to shake the ground perceptibly. The largest were equivalent to moderate earthquakes on Earth, registering magnitudes around 4 or 5. Though none of them cracked the surface dramatically, their patterns carried clues about the planet's internal structure. Its crust, mantle, and core, hidden from view since Mars's birth. Unlike Earth's quakes, which are driven by the movement of tectonic plates colliding and sliding past one another, Mars quakes arise from the planet's slow cooling and contraction. As the interior loses heat over time, it shrinks slightly, causing the brittle crust to fracture. The stresses from this contraction build until they are released suddenly as seismic waves. Some Marsquakes are also thought to occur along ancient fault lines or near regions of volcanic activity, like the towering Tharsis Plateau, home to the immense volcano Olympus Mons. Though those volcanoes are long extinct, their roots may still hold residual heat, enough to strain the surrounding rock and cause it to shift. In this way, the planet's deep memory continues to shape its present. InSight's discoveries revealed not only that Marsquakes exist, but also that Mars's interior is far more complex than once imagined. The seismic data allowed scientists to see beneath the surface, measuring how waves traveled through different layers. These observations confirmed that Mars has a core rich in iron and sulfur, a thick mantle of slowly solidifying rock, and a crust thinner than expected in some regions. Each quake that rippled through the planet acted like a natural probe, mapping its hidden anatomy. Even the tiniest tremors added to a growing picture of Mars as a world still in motion, its geological heart cooling but not yet frozen. There is something strangely human about the idea of Marsquakes, the notion that even a silent planet has a pulse. These tremors connect Mars to Earth in a subtle way, as if the two worlds share a rhythm written into the physics of their creation. For billions of years, both planets were forged in fire, shaped by impacts and heat. Earth remained alive, its interior churning with molten energy, while Mars cooled and quieted. And yet, through the faint shaking of its crust, Mars reminds us that it is not entirely gone. that something still stirs beneath its barren face. In the future, when humans finally set foot on Mars, they will likely feel these small quakes beneath their boots. They will not be dangerous, but they will be a reminder that the planet beneath them breathes, however slowly. Sensors will tremble in the dust, and astronauts may pause to listen to the low groan of the Martian ground, a sound that connects them to the deep interior of an alien world. Mars quakes are not just scientific curiosities. They are the heartbeat of a planet that still remembers its youth. In their quiet persistence, they tell us that Mars, though ancient and wounded, remains alive in its own austere, patient way. Gravity on Mars is a quiet force, gentle and restrained, far weaker than the pull that anchors us to Earth. To stand on its surface would be to feel a strange lightness, as though the body had been relieved of an invisible weight. Every movement would feel easier, every step longer and slower, as if the planet itself encouraged you to drift rather than walk. Mars's gravity is only about 38% of Earth's. A person who weighs 100 kilograms on Earth would weigh barely 38 on Mars. This simple difference changes everything, from how dust settles in the air to how mountains grow and how a person would learn to move, to live, and perhaps one day to call the place home. The weak gravity of Mars is a direct reflection of its smallness. The planet is only about half the size of Earth, and its mass is far less. Gravity, being a measure of a world's ability to hold matter close, diminishes with smaller mass and radius. Mars simply does not have enough material to exert a strong pull. The thin atmosphere, too, is a casualty of this light gravity. Over billions of years, the solar wind stripped away much of the air that once surrounded the planet, scattering it into space because Mars lacked the strength to hold it. What remains is a fragile veil of carbon dioxide, less than 1% as dense as Earth's, thin enough that liquid water cannot persist on the surface and too insubstantial to shield against radiation or cold. Yet this gentle gravity has shaped Mars in surprising and beautiful ways. Its volcanoes, freed from the crushing pull of a stronger world, could rise to extraordinary heights. Olympus Mons, the tallest mountain in the solar system, could never have existed on Earth. Under Earth's gravity, such a structure would collapse under its own weight. On Mars, however, the weak pull allowed it to grow 22 kilometers high, a monument to the freedom that light gravity grants to stone and magma. Dust storms, too, owe their persistence to this diminished force. Fine particles, once lifted by the wind, fall slowly, hanging in the air for weeks or even months, painting the sky with their reddish haze. In every detail, the planet's light gravity leaves its mark, not only on its landscapes, but on the way the planet breathes and changes. For humans, the difference in gravity would be immediately noticeable. Walking on Mars would feel like moving in slow motion, each step carrying farther, each jump soaring higher. A person could leap nearly 3 times as high as on Earth, and heavy equipment would feel unexpectedly manageable. Yet this lightness comes with hidden consequences. Over time, the human body depends on gravity to stay strong. Bones grow dense, muscles stay firm, and blood flows with rhythm because of the Earth's pull. On Mars, with its weaker gravity, astronauts would slowly lose bone mass and muscle strength, their bodies adapting to a world that asks less of them. Hearts would not need to pump as forcefully, and balance might feel uncertain at first, as if one were perpetually in the midst of a gentle fall. Still, the notion of living under such gravity carries a peculiar allure. Children born there, if humanity ever settles the red planet, would grow up taller and lighter, their steps buoyant, their play graceful in ways impossible on Earth. They would know gravity not as a burden, but as a companion that holds them softly. Their planet would shape them, just as Earth has shaped us, making their movements, their strength, and even their sense of space something uniquely Martian. In the end, Mars's weak gravity is both a gift and a challenge. It has sculpted its towering volcanoes, sustained its endless dust storms, and preserved its landscapes in slow motion, nearly untouched by time. For those who dream of walking there, it offers a glimpse of freedom, a world where every step feels like a small flight. Yet it also reminds us of how delicately we are balanced with our own planet's pull, how gravity, in all its strength or gentleness, defines what it means to belong to a world. Mars, though distant and colder than Earth, shares a familiar rhythm with our planet. It experiences seasons. Spring, summer, autumn, and winter all unfold on the red planet, shaping its landscape and atmosphere over the course of its long year. This similarity exists because Mars, like Earth, is tilted on its axis. Its tilt is about 25 degrees, close to Earth's 23.5, and it is this inclination that causes the sun's light to strike different parts of the planet more directly at different times in its orbit. As Mars travels around the sun over 687 Earth days, the shifting angle of sunlight brings about the same fundamental seasonal changes that occur on Earth, though with their own unique Martian character. The presence of seasons means that no part of Mars is exactly the same year-round. When one hemisphere tilts toward the sun, it basks in summer, while the opposite hemisphere experiences winter's long, frigid nights. 6 months later, their roles reverse. But because Mars' year is nearly twice as long as Earth's, each season lasts almost twice as long too. A Martian spring can stretch for about 190 Earth days, and its winter lingers for roughly 150. These extended periods give the seasons a slower, more drawn-out feel compared to the quick cycle of change on Earth. The thin atmosphere and greater distance from the sun mean that Martian seasons differ in intensity from those on Earth. Even at the height of summer, temperatures remain far below what we experience on our planet, often hovering well below freezing. In winter, they can plunge to minus 125 degrees Celsius near the poles. Despite this, the changes brought by the seasons are dramatic in their own way. One of the most striking transformations occurs in the polar regions, where vast caps of carbon dioxide ice expand and contract with the changing seasons. During the frigid winter, carbon dioxide from the atmosphere freezes onto the surface, causing the polar caps to grow. When spring sunlight returns, the carbon dioxide sublimates back into gas, shrinking the caps and thickening the atmosphere. This seasonal breathing of the poles affects the planet's air pressure and wind patterns across the globe. The Martian landscape itself bears the marks of the seasons. As temperatures rise in spring and summer, winds whip across the surface, lifting dust into the atmosphere and sometimes triggering massive dust storms that can envelop the entire planet. These storms can last for weeks and dramatically alter the appearance of Mars from space. In autumn and winter, frost forms on rocks and dunes, painting the surface with thin layers of ice that vanish again with the return of warmth. Even the color of the atmosphere changes slightly with the seasons, as shifting amounts of dust and ice particles scatter sunlight in different ways. For future explorers and scientists, Mars' seasonal cycle is more than a curiosity. It is a vital factor to understand. Any attempt to grow plants, generate power, or build shelters will depend on knowing how temperatures, sunlight, and atmospheric conditions change over the Martian year. The seasons also influence where and when water ice is most accessible, which could be essential for human survival. By studying these cycles, scientists gain insight into Mars' climate history and how it has changed over time, possibly even revealing periods when the planet was warmer and wetter. The fact that Mars has seasons like Earth is a reminder of the shared dynamics that shape planets orbiting the same star. Despite its thin air, rusty deserts, and bitter cold, Mars turns on a tilted axis beneath the Sun just as Earth does, giving rise to the same fundamental pattern of change. Each spring and summer, each autumn and winter, links our world to this distant one. It is a connection that makes Mars feel a little less alien. A planet where, beneath a salmon-colored sky, time is still measured in the quiet turning of the seasons. On Earth, the sky glows red and orange when the sun sinks below the horizon, but on Mars, the opposite happens. As evening falls on the red planet, its dusty sky takes on a pale, cool blue around the setting sun. A haunting reversal of what we know. The rest of the heavens remain tinted in rusty oranges and browns, but the light near the sun softens into a narrow circle of blue, fading gently into the surrounding twilight. It is a quiet, almost otherworldly sight. The sun descending into a blue halo in a world otherwise painted in red. The reason for this unusual effect lies in the Martian atmosphere and its ever-present dust. Mars' air is extremely thin, only about 1% as dense as Earth's, and filled with fine particles of iron-rich dust that scatter sunlight differently than our atmosphere does. On Earth, molecules of nitrogen and oxygen scatter short blue wavelengths of light more than the longer red ones, which is why our daytime sky is blue and our sunsets red. As the sun lowers, its light passes through more air, scattering away the blue light and leaving behind the warmer hues. Mars, however, is covered in dust so fine that it interacts with sunlight in the opposite way. The reddish dust particles are about the same size as the wavelength of visible light, and they scatter red light more effectively than blue. During the day, this scattering fills the sky with a reddish or butterscotch tint, the signature color of Mars. But at sunset, when sunlight must pass through a much greater distance of this dusty air, the blue light is scattered forward rather than away, concentrating around the sun itself and painting the horizon in cool tones. For a moment, as the sun dips lower, the Martian landscape is transformed. The long shadows of rocks stretch across the crimson soil, while the distant sky glows faintly blue, fading to gray and then deep brown as night takes hold. The transition happens quickly. Mars' thin atmosphere cannot hold light for long. Within minutes, the blue fades, leaving the surface in the dim orange light of twilight before darkness falls completely. The sight is both alien and strangely familiar, reminding us that the same sun shines on two worlds, yet the ways it touches their skies are shaped by the nature of each planet. The blue sunsets of Mars are not just a poetic curiosity. They reveal much about the planet's air and dust. Scientists studying images taken by rovers like Spirit, Opportunity, and Curiosity have used this effect to understand how particles in the Martian atmosphere scatter light. The hue and brightness of the sunset tell researchers the size and density of airborne dust, helping them track changes during dust storms and seasons. These blue twilights are, in a sense, natural experiments, windows into the physics of Mars skies. For future human explorers, witnessing a Martian sunset would be a moment of quiet wonder. Standing in the cold, thin air, they would watch the same sun they knew from Earth sink into a different world's horizon, wrapped not in fiery reds but in serene blues. It would be a reminder that beauty exists even in harsh places, and that familiar phenomena can appear utterly transformed under new conditions. The blue sunset of Mars is a perfect symbol of the planet itself, a blend of the known and the alien. It looks almost like home, yet not quite. The dust that gives Mars its red face also gives its evenings their unexpected blue. In that fleeting glow lies a story of physics, distance, and atmosphere, but also one of quiet wonder. A small, beautiful inversion that captures the mystery of a world so close to ours, yet so entirely its own. Mars is home to a canyon so vast and deep that it dwarfs anything found on Earth. Known as Valles Marineris, this enormous system of canyons stretches more than 4,000 kilometers across the Martian surface, about the distance from Spain to Ukraine, and plunges as deep as 7 to 10 kilometers in some places. That makes it nearly 10 times longer and several times deeper than the Grand Canyon. It is not a single trench but a sprawling network of valleys, cliffs, and chasms that carve a dramatic scar across the Martian equator. Seen from orbit, Valles Marineris is so large that it dominates the planet's surface features, a vast geological wound that tells the story of Mars' ancient and dynamic past. The origin of this canyon is still debated, but scientists believe it formed differently from most canyons on Earth. Our planet's great gorges are usually carved by rivers over millions of years, but Valles Marineris likely began as a colossal rift, a place where Mars' crust was pulled apart by immense tectonic forces. Early in Mars' history, volcanic activity in the nearby Tharsis region caused the crust to bulge upward. As the ground swelled, it stretched and cracked, creating massive fractures. Over time, these fissures widened and deepened, and landslides, erosion, and possibly water flow helped sculpt them into the vast canyon system we see today. This makes Valles Marineris not only a natural wonder, but also a record of the planet's internal forces and changing surface. The scale of the canyon is difficult to comprehend. In places, it is more than 200 kilometers wide, and its walls rise higher than Mount Everest towers above sea level. The cliffs and terraces expose layers of Martian rock that span billions of years, providing scientists with a rare window into the planet's geological history. By studying these layers, researchers hope to learn how Mars evolved, how its crust formed, and whether water once flowed through its canyons. There are signs that liquid water might have contributed to the shaping of some sections, with channels and sediment deposits suggesting that water, ice, or even ancient lakes may once have existed within its depths. Valles Marineris is not only a geological marvel, but also a potential treasure trove for future exploration. Its towering cliffs and deep valleys offer exposed rock layers that could reveal vital information about the planet's past environment and climate. If Mars ever hosted microbial life, traces of it might be preserved in these ancient rocks, shielded from harsh surface conditions. The canyon's sheltered environment could also provide some protection from radiation, making it a potential site for future human outposts. The canyon's immense size also shapes local weather and atmospheric conditions. Winds sweep through its depths, creating unique microclimates that differ from the surrounding plains. Temperature changes from day to night can be more extreme within the canyon, and dust often gathers in its lower reaches. These variations make Valles Marineris not only an impressive landmark, but also a natural laboratory for studying how Mars' thin atmosphere interacts with its rugged terrain. Valles Marineris stands as one of the most dramatic features in the solar system, a monument to the powerful forces that have shaped Mars over billions of years. Its sheer scale reminds us that even a planet smaller and quieter than Earth can produce landscapes of breathtaking magnitude. It is a place that challenges our imagination. A canyon so deep and long that if it were on Earth, it would stretch across an entire continent. As we continue to explore Mars, Valles Marineris will remain one of its most compelling destinations, a vast and ancient chasm that holds the secrets of a planet's past and perhaps clues to its potential for life. Long before Mars became the cold, quiet planet we see today, it endured a moment of unimaginable violence. an impact so vast that it reshaped half the world. This colossal scar, known as the Hellas Basin, is the largest impact basin in the entire solar system, a vast depression that measures more than 2,000 kilometers across and up to 8 kilometers deep. To grasp its scale is to realize that if one were to stand on its floor, the basin's rim would rise higher than the tallest mountains on Earth, stretching far beyond the horizon. It is not merely a crater. It is an ancient wound that tells the story of a world transformed by catastrophe. Hellas lies in the planet's southern hemisphere, a pale oval visible even through small telescopes from Earth. It is the relic of an impact that likely occurred more than 4 billion years ago, when the solar system was still young and chaotic. In those days, countless asteroids and comets hurtled through space, colliding with the inner planets in a relentless bombardment. One of those bodies, perhaps a massive asteroid or a fragment of a protoplanet, struck Mars with a force so great that it released energy equivalent to millions of hydrogen bombs. The blow excavated an enormous cavity in the planet's crust, scattering debris across the hemisphere and sending shock waves that rippled through the interior. What remained was the Hellas Basin, a scarred and sunken plain that would forever alter Mars's geography and history. Over time, winds and dust softened the outlines of the basin, but its immensity is still unmistakable. The floor of Hellas is smoother and brighter than the surrounding terrain, partly because fine dust and frost collect there. During the Martian winter, the basin becomes a trap for cold air, forming frost and ice that glint under the pale sunlight. In certain seasons, carbon dioxide snow can blanket the lowlands, creating patterns that shift with the changing temperature. Because Hellas sits deep below the average elevation of Mars, its air pressure is significantly higher than elsewhere on the planet. Still thin by earthly standards, but dense enough to hold faint mists and clouds that drift across its expanse. It is one of the few places on Mars where the conditions might briefly allow liquid water to exist, at least for a fleeting moment, before freezing or evaporating into the dry air. The impact that formed Hellas Basin did more than carve out a depression. It may have influenced the entire structure of Mars. Some scientists believe that the event helped tilt the planet's axis or contributed to the stark difference between the northern and southern hemispheres. The northern plains being smooth and low, the southern highlands rugged and cratered. The collision could have triggered volcanic activity, heating the crust and releasing gases that thickened the ancient atmosphere. In this way, a single cosmic event might have played a role in shaping Mars's early environment, perhaps even creating temporary conditions suitable for liquid water to flow across its surface. Today, the Hellas Basin stands as a silent monument to that deep past. Its rim is fractured and eroded, its floor coated in dust and ancient sediments, yet it remains one of the most striking landscapes in the solar system. Orbiters have mapped its canyons, dunes, and strange layered deposits, revealing evidence that wind, ice, and perhaps even water have all had their turn in sculpting this immense bowl. For planetary scientists, Hellas is both a window and a mirror, showing not only how Mars evolved but how impacts have shaped all the rocky worlds, including our own. To imagine standing there is to feel the weight of cosmic history. The sky above would be pale and hazy, the horizon distant and indistinct. The air would be cold but slightly thicker than elsewhere on Mars, and the sunlight would filter weakly through dust and frost. Beneath your feet would lie the frozen remains of an ancient cataclysm, a reminder of how fragile and violent the making of a planet can be. Hellas Basin is more than the largest crater in the solar system. It is the echo of creation itself, frozen in stone, enduring long after the fire that formed it went dark. Mars, the fourth planet from the Sun, is often called Earth's smaller sibling, and with good reason. Its diameter is only about half that of Earth, roughly 6,779 kilometers compared to Earth's 12,742, and its volume is just about 15% of our planet's. This difference in size has shaped nearly every aspect of Mars, from its gravity and atmosphere to its geology and potential for life. The two worlds share many similarities, but Mars' smaller scale has led it down a very different evolutionary path. Being half the size means Mars has much less mass than Earth, and with that comes weaker gravity. A person weighing 70 kilograms on Earth would weigh only about 26 kilograms on Mars. This lower gravity has profound consequences. It affects how the planet holds onto its atmosphere, or rather, how it struggles to do so. Billions of years ago, Mars likely had a thicker atmosphere and flowing water on its surface, but its smaller size meant its core cooled faster than Earth's. As the internal heat faded, the magnetic field that once protected Mars from solar winds weakened and vanished. Without this shield, the sun's radiation stripped away much of the atmosphere, leaving behind a thin veil of mostly carbon dioxide that offers little protection and traps little heat. The planet's small size also influences its surface and interior. Mars cooled more rapidly than Earth, which slowed its geological activity over time. Today, it lacks the active plate tectonics that continually reshape Earth's surface. Yet, despite its size, Mars boasts some of the most colossal landforms in the solar system. Olympus Mons, a towering shield volcano, rises about 22 kilometers high, nearly 3 times the height of Mount Everest. Its immense size is partly due to Mars' weaker gravity and lack of tectonic motion. On Earth, moving plates would carry volcanic hotspots away, forming chains of volcanoes. On Mars, the crust remains stationary over the hotspot, allowing lava to pile up in one place over millions of years. The reduced size and gravity also mean that Mars' atmosphere can't support large bodies of liquid water on its surface today. Any exposed water quickly evaporates or freezes. Still, the planet's landscape shows evidence that rivers, lakes, and perhaps even oceans once existed. These features formed when Mars had a thicker atmosphere and a warmer climate, conditions made possible during the planet's early history before it lost much of its internal heat and protective magnetic field. If Mars had been larger, closer in size to Earth, it might have retained these conditions longer, possibly sustaining life. Mars' small size affects not only its physical properties but also how humans might one day live there. The lower gravity would change how our bodies function over long periods. Muscles and bones might weaken without the constant pull we experience on Earth. Yet the reduced gravity would also make construction easier and launches from the surface more energy efficient, a useful advantage for future explorers and settlers. Even the Martian sky and weather are shaped by its size. The thin atmosphere, unable to hold much heat, allows temperatures to swing dramatically between day and night. Dust storms can engulf the entire planet, driven by winds that, though weak by Earth's standards, face little resistance from the sparse air. Mars' smaller size and slower rotation also contribute to longer days than Earth's, about 24.6 hours, and to seasons that last nearly twice as long. Mars may be half Earth's size, but its smallness is part of what makes it fascinating. It is a world shaped by its limits, a planet where a weaker grip on heat and air has sculpted a harsh, cold environment, yet one that still echoes with traces of a warmer, wetter past. Its size reminds us how even small differences in planetary scale can lead to profoundly different destinies. In the story of Mars, being half the size of Earth has defined not just its appearance, but its entire history and character. A smaller planet with a vast story to tell. There was a time billions of years ago When Mars was not the cold, silent world it is now, but a living planet in its own way, alive with heat, motion, and energy flowing deep within its core. In that distant age, Mars possessed a magnetic field, a vast invisible shield like Earth's, born from the movement of molten metal in its interior. It wrapped the planet in protection, deflecting the fierce solar wind and preserving its atmosphere. Beneath that shelter, water could flow freely across the surface, clouds could gather, and perhaps life itself had a chance to emerge. The remnants of that long-lost magnetism still linger today, frozen in ancient rocks, the last whispers of a force that once gave Mars a warmer and more forgiving face. A magnetic field is the signature of a living planet's heart. On Earth, it arises from the motion of molten iron in the outer core, swirling and convecting as the planet rotates, generating electric currents that create a global magnetic shield. This field stretches outward, forming a magnetosphere that protects the planet from the relentless stream of charged particles emitted by the Sun billions of years ago. Mars's core, too, was molten and dynamic. The planet was still young, its interior hot with the energy of formation and radioactive decay. As the metallic elements churned beneath its crust, Mars generated a strong magnetic field of its own, powerful enough to leave its mark in the rocks that solidified during that era. The magnetized patterns we detect today are faint echoes of that ancient dynamo, preserved like fossils of an invisible past. But something changed. Over time, Mars began to cool. The smaller a planet is, the faster it loses heat, and Mars, barely half the size of Earth, was no exception. As its interior cooled, the molten metal in its core gradually solidified, halting the convective motion that sustained its magnetic field. Without that inner movement, the dynamo died. The magnetic shield weakened and eventually vanished, leaving the planet exposed to the solar wind. Stripped of its protection, Mars's atmosphere began to erode. The sun's charged particles battered the upper layers, carrying them off into space atom by atom. What had once been a thick, warm atmosphere capable of supporting liquid water was reduced to the thin, frigid veil we see today. The rivers dried, the lakes froze, and the planet entered its long winter of stillness. The consequences of this loss were profound. Without its magnetic field, Mars could no longer sustain the conditions that might have nurtured life. Its surface, once potentially habitable, became barren and hostile, bathed in radiation. Yet the traces of its former vitality remain etched across the landscape. Vast dried riverbeds, delta formations, and mineral deposits all testify to a time when Mars had a thicker atmosphere and a stable climate. Deep in its crust, magnetic anomalies, localized regions of magnetized rock, reveal the pattern of the ancient field that once encircled the planet. These relics, mapped by orbiters, form ghostly outlines of Mars's magnetic memory, reminders that the planet once had a heart that beat with fire. For scientists, the story of Mars's lost magnetism is not just a tale of one planet's decline but a lesson in planetary fate. It shows how delicate the balance of habitability can be, how a small shift deep within a planet can alter the destiny of everything above. It reminds us that a world's surface is shaped as much by what lies unseen beneath it as by the forces that act upon it from without. The death of Mars's magnetic field turned a once Earth-like world into a frozen desert, a transformation that speaks of both fragility and inevitability in the life cycle of planets. And yet, in that loss, Mars offers us a mirror. Its silent plains and magnetized rocks tell us that even worlds can grow old, their hearts cooling as time stretches on. To study Mars is to study our own planet's possible future, to imagine, perhaps billions of years from now, when Earth's core might also slow, when its own magnetic field fades, and the protective veil around our home thins. Mars shows us what happens when a planet's heart stops beating, and in doing so, it makes us cherish the warmth and vitality of the one that still does. Mars is a planet of shifting balance, its axis tilting and wobbling over vast stretches of time in ways far more dramatic than Earth's gentle sway. While Earth's axial tilt, the angle between its rotational axis and its orbital plane, varies only slightly, keeping its seasons relatively stable, Mars leans and straightens in wild cycles that can transform its entire climate. Over millions of years, the tilt of Mars has swung from as little as 15 degrees to more than 35 degrees, and possibly even beyond 45 in its distant past. Each shift reshapes the way sunlight falls across the planet, changing temperatures, moving ice, and rewriting the rhythm of its seasons. This instability arises because Mars lacks a large moon like Earth's to steady it. Our moon acts as a gravitational anchor, keeping Earth's tilt within a narrow range. Mars, however, has only two tiny moons, Phobos and Deimos, too small to exert much influence. As a result, the gravitational tugs of the Sun and neighboring planets, especially Jupiter, can slowly pull Mars' axis into new positions over geological timescales. The outcome is a planet whose poles wander, whose equator drifts, and whose climates shift again and again, like a pendulum swinging through deep time. When the tilt of Mars increases, its poles lean more sharply toward the Sun during their respective summers, causing the polar regions to warm. Vast amounts of ice may melt or sublimate into the atmosphere, thickening it and increasing surface pressure. In those high-tilt eras, water vapor and carbon dioxide could circulate more freely, possibly forming clouds, frost, or even temporary flows of liquid water at lower latitudes. The once frozen polar regions might release gases that trap heat, creating a milder climate closer to the equator. If microbial life ever existed there, such times might have offered brief windows of habitability, when liquid water could persist on the surface. In contrast, when the planet's tilt decreases, the poles receive less sunlight and plunge into deeper, longer winters. Ice expands outward from the poles, burying parts of the surface beneath frost and snow. The atmosphere thins as carbon dioxide freezes out and settles as ice at the poles. The planet becomes colder, drier, and dustier, locked once more in a deep freeze. During these low-tilt periods, Mars looks much like it does today, an icy desert, wrapped in a thin, frigid atmosphere. The record of these changes lies written in the Martian landscape. Layered deposits at the poles preserve traces of different climatic eras, alternating bands of ice and dust that mark shifts in tilt, much like rings in a tree. Each layer tells of a time when the planet's orientation changed, altering the amount of sunlight and warmth each region received. By studying these layers, scientists can reconstruct Mars' climate history, revealing patterns of warming and cooling that stretch back millions of years. The idea that an entire planet's climate can swing so drastically because of its wobbling axis is both fascinating and sobering. On Earth, even small changes in tilt have influenced ice ages and warm periods. On Mars, where the tilt can shift by tens of degrees, the consequences are far more profound. Whole regions can change from icy wastelands to temperate plains and back again. It is a world in motion, not in space alone, but in orientation and balance, forever caught between stability and chaos. Today, Mars stands in a relatively moderate phase of its tilt, about 25 degrees, similar to Earth's. But in the deep future, its axis will again move, reshaping its climate anew. The planet's changing tilt reminds us that time and gravity sculpt not only landscapes but entire worlds. Mars, with its restless axis, shows that the balance of a planet is fragile, and that even the slowest cosmic motions can alter the face of a world, turning ice into vapor, deserts into valleys, and climates into fleeting memories of warmth beneath a distant sun. Long ago, before the planet became the frozen desert we know today, Mars was a world of flowing rivers, glimmering lakes, and perhaps even vast northern seas. Its surface, now etched with the scars of dryness and time, bears silent testimony to the presence of liquid water that once shaped its valleys and plains. The red planet was not always so red, nor so barren. Beneath its dusty hue lie minerals that could only have formed in the presence of water, clays, sulfates, and hydrated salts, each particle a whisper of a time when Mars had a climate capable of sustaining liquid flow across its surface. When we look upon the winding channels that snake across the Martian terrain, they speak the language of erosion. These sinuous valleys resemble the dried beds of ancient rivers on Earth, carved by persistent currents that once carried sediment and reshaped the land. The evidence is more than visual suggestion. High-resolution images from orbiters, such as NASA's Mars Reconnaissance Orbiter, reveal deltas where water once deposited layers of silt at the mouths of long-lost lakes. In places like Jezero Crater, scientists can read the story of Martian hydrology as if turning the pages of a book, each stratum recording a pulse of liquid life in a world that has since fallen silent. Billions of years ago, Mars had a thicker atmosphere. It likely held enough carbon dioxide to trap warmth and maintain surface temperatures above freezing for long stretches of time. The Sun, younger and dimmer than today, still offered enough energy to sustain a tenuous but viable climate. Rain might have fallen on those ancient plains. Water pooled in basins, eroded crater walls, and carved out networks of tributaries that converged into broad valleys. The planet was alive in its own way. Geologically active, its volcanoes spewing gas and heat into the air, its magnetic field still flickering, offering some protection from solar radiation. But Mars was fragile. Over time, its magnetic field weakened and then vanished. Without that shield, the solar wind began to strip away its atmosphere atom by atom. The pressure dropped, and with it the planet's ability to hold liquid water on its surface. What had once been rivers turned to ice or evaporated into space. The seas receded, leaving behind salt flats and cracked deltas. The air grew thin and cold. The red dust that now sweeps across the planet is the remnant of a world that once glistened under a blue sky. And yet, the traces remain stubbornly persistent. In the polar regions, ice caps made of water and carbon dioxide still glint beneath the sun. Beneath the surface, deposits of frozen water hide in shadowed craters and underground aquifers, preserved through eons of desolation. In recent years, transient dark streaks, called recurring slope lineae, have appeared seasonally on Martian cliffs, possibly formed by briny water seeping through the soil before evaporating in the thin air. Though these traces are fleeting, they hint that Mars still clings to its ancient relationship with water, even if only in brief, ghostly moments. For scientists and dreamers alike, this knowledge changes everything. Water is the prerequisite for life as we understand it. If Mars once had enough of it to shape its surface and fill its basins, then perhaps it also nurtured life in some microbial form. The discovery of ancient riverbeds and lakebeds transforms the question from did water ever exist there, to what else might have existed with it. Each rover that touches the Martian soil, Curiosity, Perseverance, and those yet to come, carries this question as its mission's quiet heart. They study sediments, drill into rock, and search for organic compounds, all in pursuit of a story that began billions of years ago when Mars was warm and wet. In the end, the tale of Martian water is not merely about a distant planet. It is about our longing to understand how worlds change, how they live and die, and whether somewhere in that long cosmic history we might glimpse a reflection of our own planet's fragile journey through time. Long before Mars became the cold, barren desert it is today, it might have been a world that could sustain life. Not the kind of life that walks or breathes, but tiny, unseen microbes. The evidence lies scattered across its surface, etched in dry riverbeds, layered in rocks, and preserved in minerals that once formed in the presence of water. Billions of years ago, Mars may have had everything simple organisms needed to survive. Liquid water, a thicker atmosphere, a warmer climate, and essential chemical ingredients. It might not have been a lush paradise, but in its youth, Mars could have been habitable in ways that echo the earliest days of life on Earth. Scientists believe that about 3 to 4 billion years ago, Mars had flowing rivers, lakes, and perhaps even shallow seas. Ancient valleys carved into the landscape suggest that water once moved freely across the surface, shaping channels and depositing sediments. Rovers like Curiosity and Perseverance have found evidence of clay and sulfate minerals, materials that form only in wet conditions. These discoveries point to a time when the planet's surface was not dry and frozen but active and dynamic, with conditions that could have sheltered microbes. The presence of these minerals also indicates that the water was not too acidic or salty, a key factor in creating a stable environment for life. The Martian atmosphere, now thin and unable to retain much warmth, was once much denser. A thicker layer of carbon dioxide could have trapped heat and created a greenhouse effect, allowing temperatures warm enough for liquid water to exist. In such an environment, simple life forms, if they ever arose, might have thrived in lakes, subsurface aquifers, or hydrothermal vents near volcanic regions. On Earth, microbes have been found living in boiling springs, deep underground rocks, and even frozen Antarctic lakes, proving that life can adapt to nearly any environment. If it could happen here, it is not impossible that it once happened on Mars too. Even as Mars began to lose its atmosphere and cool, some parts of the planet might have remained habitable underground. Below the surface, water could have stayed liquid for longer, insulated from the harsh radiation that bombards the planet. Deep beneath the Martian crust, chemical reactions between rock and water, such as those involving hydrogen and methane, could have provided energy sources for microbes, much like they do for certain bacteria on Earth today. In this hidden world, life could have persisted long after the surface became dry and frozen. The search for signs of this potential life continues. The Curiosity rover has found organic molecules, the basic building blocks of life, preserved in Martian rocks. While these molecules alone do not prove that life existed, their presence shows that the chemistry of life was at least possible there. Perseverance, exploring the Jezero crater, is studying sediments that once lay at the bottom of an ancient lake, collecting samples that will one day be returned to Earth. If those rocks contain fossilized microbes or chemical patterns left by biology, they could answer one of humanity's oldest questions. Are we alone? Even if no life ever developed on Mars, the fact that it could have been habitable is deeply significant. It shows that the ingredients for life are not unique to Earth, that under the right conditions, another planet can come close to supporting it. Mars stands as a reminder that habitability does not always mean a thriving biosphere. Sometimes it means potential, a brief window in time when everything necessary for life came together but may never have taken that next step. To imagine ancient Mars is to picture a world on the edge of possibility. A place where rivers once flowed under a warmer sky, where perhaps beneath the soil, tiny forms of life stirred in the dark. Whether those microbes ever existed or not, the story of Mars tells us that life, or the chance for it, may not be confined to one small blue planet but scattered among the stars, waiting to be found. Among the countless rocks that fall from space to Earth, a small and rare group carries a story that begins far away, on Mars. Scattered across deserts and frozen plains, scientists have discovered meteorites that were once part of the Martian surface. These stones, known as Martian meteorites, are fragments of Mars itself, flung into space millions of years ago, and eventually finding their way across the vast gulf between planets. They are silent travelers, carrying within them the chemical fingerprints of another world, offering a direct physical link between Earth and Mars. The journey of these rocks begins with violence. When a large asteroid or comet slams into the surface of Mars, the impact releases enormous energy, enough to blast pieces of Martian rock high above the planet. Some fragments are ejected with such speed that they escape Mars' gravity entirely. For centuries or millennia, these stones drift through space, orbiting the sun alongside the planets. A few of them, by chance and the slow pull of gravity, cross paths with Earth. When they finally enter our atmosphere, they streak through the sky as fireballs before falling to the ground, often landing in remote places where they can remain untouched for thousands of years. Identifying a Martian meteorite is no easy task. Out of the tens of thousands of meteorites found on Earth, only a few hundred have been confirmed to come from Mars. Scientists recognize them by their chemistry and trapped gases, which match the measurements taken by landers and rovers on the Martian surface. The ratio of noble gases, argon, xenon, and krypton, in these rocks is identical to that in Mars' atmosphere, as first recorded by the Viking missions in the 1970s. This match is a cosmic signature, proof that these stones truly came from the red planet. They are pieces of another world lying quietly on ours. These meteorites vary in age and composition. Some are ancient, formed billions of years ago when Mars was warmer and wetter, while others are relatively young, solidifying just a few 100 million years ago. Many are made of volcanic basalt, remnants of lava flows that once covered Martian plains. Others contain minerals altered by water, hinting at interactions with liquid long ago. In their microscopic textures, scientists have found tiny pockets of glass, minerals rich in iron, and even inclusions that once held traces of gas and possibly organic molecules. Each sample is a record of a moment in Martian history, a clue to what the planet once was. One of the most famous Martian meteorites, known as ALH 84001, was discovered in Antarctica in 1984. When scientists studied it in the 1990s, they found structures that some interpreted as fossil-like, tiny shapes that resembled bacteria. Though later studies showed these shapes could have formed through natural, non-biological processes, the discovery sparked enormous interest and debate about whether life could have once existed on Mars. Since then, each new Martian meteorite has been examined for signs of past habitability, and though no proof of life has been found, the stones continue to inspire curiosity and hope. These meteorites are more than scientific samples. They are ambassadors from a distant world. They show that the exchange of material between planets is not impossible, that pieces of Mars can reach Earth, and perhaps long ago, the reverse might also have occurred. Some scientists even speculate that life, if it ever began on Mars, could have traveled to Earth aboard such rocks, carried safely within before landing here to take root. Whether or not that is true, the Martian meteorites remind us that the planets of the solar system are not isolated, but part of a greater cosmic network, connected by the slow, random movements of stone across space. To hold a Martian meteorite is to hold a piece of another planet, one that has journeyed millions of kilometers, survived the emptiness of space, and fallen through Earth's sky. It is both alien and familiar, a fragment of a red desert world that continues to whisper stories of its distant home. Through these ancient travelers, Mars reaches across the void to touch Earth, linking two worlds that have long watched each other across the dark. The surface of Mars, beneath its silent red plains and windswept dunes, hides a constant danger invisible to the eye. It is bathed in radiation, a steady rain of energetic particles from the sun and distant stars that sweeps across the planet unfiltered. Unlike Earth, which is shielded by a thick atmosphere and a powerful magnetic field, Mars has no real protection. Its thin air and weak magnetic remnant allow cosmic and solar radiation to reach the surface freely, making the entire planet radioactive in a way no place on Earth naturally is. It is one of the most defining and hazardous features of Mars, a quiet, invisible force shaping its landscape and the possibilities for life. Billions of years ago, Mars likely had a magnetic field like Earth's, generated by the movement of molten iron in its core. That field would have deflected much of the charged radiation from space. But as the planet cooled and its core solidified, the global magnetic shield faded away. The solar wind, a constant stream of particles from the sun, then began stripping away the upper layers of the atmosphere. Over time, Mars was left with only a thin veil of air, less than 1% as dense as Earth's. Without its atmospheric and magnetic barriers, radiation from space now strikes the Martian surface almost unhindered. Every day, the planet absorbs doses of cosmic and solar radiation that would be deadly to humans over long exposure. The source of this radiation comes from two main places: the sun and beyond the solar system. Solar energetic particles are bursts of high-energy protons released during solar flares and coronal mass ejections. Galactic cosmic rays, on the other hand, come from exploding stars far across the Milky Way. Both are capable of penetrating deep into the Martian soil, ionizing atoms and breaking molecular bonds along the way. The constant bombardment alters the chemistry of the surface, destroying fragile organic molecules that might once have hinted at ancient life. Even just a few centimeters below the soil, these molecules are degraded over time, making the search for life's traces more difficult. To find better preserved evidence, scientists now look deeper underground, where the radiation cannot reach as easily. For any future human explorers, this radiation poses a serious challenge. On Mars, a person standing unprotected on the surface would receive several hundred times more radiation per year than someone on Earth. Extended exposure could increase the risk of cancer and cause damage to tissues and DNA. Because there is no magnetic field to deflect it and no thick air to absorb it, the radiation penetrates everything it touches: rock, metal, or living cells. Shielding against it requires ingenuity. Habitats might need to be built underground, covered with Martian soil, or protected by layers of water or specialized materials to block the incoming particles. Even the rovers that roam Mars must endure this invisible assault. Their electronic systems are designed to withstand radiation damage, but over time, exposure can degrade circuits and sensors. Despite this, they continue their work, measuring radiation levels and helping scientists understand what life, mechanical or biological, might need to survive there. Instruments aboard the Curiosity rover and the Perseverance rover regularly record how radiation changes with solar activity, dust storms, and atmospheric pressure, giving humanity a clearer picture of Mars' harsh environment. The radioactivity of Mars' surface is both a barrier and a clue. It reminds us that the planet, though once more Earth-like, has long since lost the protections that made our world habitable. Yet it also points to a history of change, a time when Mars had a magnetic field, thick air, and perhaps even water flowing freely across its plains. The radiation that now sterilizes its surface once had no way to reach it. In this way, the radioactive glow of Mars is not just a hazard but also a relic of its transformation, a silent witness to the planet's long and lonely evolution from a warmer world to the cold, exposed desert it has become. Mars is a world of extremes, and few features of its environment are as striking as the dramatic variation in temperature. On this cold, dry planet, the difference between day and night can be enormous, sometimes more than 100 degrees Celsius. Under the pale light of the distant sun, the surface can briefly warm to a pleasant 20 degrees Celsius in the afternoon, but after sunset, the heat vanishes almost instantly, plunging the temperature to -70 degrees Celsius or even lower before dawn. This sharp contrast defines daily life on Mars and reveals much about the planet's thin atmosphere, its distance from the sun, and its fragile balance of heat and cold. The cause of these drastic temperature changes lies first in Mars' atmosphere, which is extremely thin, less than 1% the density of Earth's. On Earth, the atmosphere acts like a blanket, trapping warmth near the surface and keeping nighttime temperatures relatively stable. Mars lacks this protection. The air is too light to hold heat, so when the sun's rays fade, the warmth radiates quickly back into space. As a result, while the ground may heat up rapidly under the sun, it cools just as fast once darkness falls. The thin air also means that heat cannot circulate efficiently, so areas in sunlight can be far warmer than those in shadow, even within the same region. Mars' distance from the sun adds to this effect. Being about 1.5 times farther from the sun than Earth, Mars receives only about 43% as much sunlight. The reduced energy limits how much the planet can warm during the day. At the equator, the surface may reach temperatures comfortable by human standards at midday, but just a few hours later, the same region freezes. Near the poles, the contrast is even more extreme, with winter temperatures dropping to -125 degrees Celsius. These vast swings make Mars a planet of cold extremes, a place where warmth is fleeting and fragile. Dust also plays a role in the planet's temperature shifts. Fine red dust covers much of the surface, and when strong winds lift it into the atmosphere, it can scatter and absorb sunlight, changing how heat spreads. During massive dust storms, the surface can cool while the atmosphere above warms slightly, creating strange and temporary weather patterns. When the storms pass and the dust settles, the balance shifts again. This constant interplay between sunlight, dust, and air gives Mars a restless, ever-changing climate. The drastic temperature variations have deep implications for the planet's surface and potential for life. When the ground cools rapidly at night, frost can form even near the equator. This frost is often made of carbon dioxide rather than water, freezing directly out of the thin air. Over time, such temperature-driven processes help shape the landscape, cracking rocks and eroding surfaces as they expand and contract with each daily cycle. For scientists, these changes provide clues about how Mars' surface evolves, even without liquid water or active plate tectonics. For future human explorers, these temperature swings present a major challenge. Habitats, Suits and machines must withstand both moderate warmth and extreme cold within the span of a single day. Electronics and batteries must be designed to function despite constant freezing and thawing. The drastic fluctuations could even make planning outdoor work complex, as conditions change rapidly with the setting sun. Mars' wild temperature shifts remind us how different it truly is from Earth. Here, our thick atmosphere, oceans, and clouds keep temperatures relatively stable, but on Mars, the balance is delicate and exposed. The warmth of the day and the chill of the night define its rhythm, creating a world where the surface never truly settles into comfort. These variations are not just environmental details. They are part of what makes Mars both beautiful and inhospitable. A frozen desert where sunlight and darkness wage a silent, endless battle for control of the land. Among all the worlds that circle our sun, Mars stands out as the one that most resembles home, even in its desolation. It is cold, dry, and far from hospitable, yet it holds a strange familiarity, a landscape shaped by wind and dust, mountains and valleys, skies and sunsets. It is this resemblance, faint though it may be, that has made Mars the prime candidate for future human missions. For generations, it has captured the human imagination as the next frontier, the place where our species might first set foot beyond Earth and begin the long experiment of living on another world. Mars offers both promise and peril. It is close enough to reach within a human lifetime, yet distant enough to test every limit of our technology and endurance. At its nearest, it lies about 55 million kilometers from Earth, a journey that would take 6 to 9 months with current propulsion systems. Unlike the airless Moon, Mars has a thin atmosphere, mostly carbon dioxide, that can provide some protection from radiation and even be harnessed as a resource. Its day is only slightly longer than ours, its seasons familiar in rhythm though colder and harsher, and its gravity, though weaker, is strong enough to allow movement and work without the disorienting float of space. These similarities have made it a natural target for exploration, a place where the idea of human presence seems just within reach. For decades, robotic explorers have paved the way, preparing the ground for those who will follow. Rovers like Spirit, Opportunity, Curiosity, and Perseverance have traversed the planet's surface, sending back images of orange plains and rocky hills that feel strangely terrestrial. They have studied the soil, analyzed rocks, and searched for traces of ancient water, evidence that Mars was once more hospitable than it is today. Orbiters have mapped its canyons, its polar ice caps, and the remnants of riverbeds carved by long-vanished streams. Each mission adds to our understanding of what it would take to survive there. How to extract water from frozen ground, how to generate oxygen from the atmosphere, how to endure the cold and the thin air. The challenges are immense. The Martian atmosphere is less than 1% the density of Earth's, too thin to breathe and too weak to block cosmic radiation. Temperatures can plunge to minus 120 degrees Celsius at night. Dust storms can engulf the entire planet, darkening the sky for weeks. Communication with Earth would be delayed by several minutes, making real-time contact impossible. Any crew that ventures to Mars would have to be self-reliant, capable of producing air, water, and food from the planet's sparse resources, and of surviving months of isolation millions of kilometers from home. Yet these very obstacles are what make the dream compelling. Mars is not a destination for ease. It is a test of resilience, ingenuity, and the human desire to endure. Plans for such missions are no longer confined to science fiction. NASA, along with international partners and private companies, is developing the technologies that will make a journey to Mars possible. Powerful new rockets, habitats that can withstand radiation, and systems for recycling air and water. The Artemis missions to the Moon are a rehearsal, a way to refine the methods that will later carry humans farther. SpaceX, with its ambitious Starship program, envisions fleets of reusable spacecraft capable of ferrying settlers to the Red Planet, building the first permanent base beyond Earth. The timeline is uncertain, but the intention is clear. The first footsteps on Mars will mark a new chapter in human history. To imagine that moment is to feel both awe and humility. A human standing on Mars, looking back at the faint blue glow of Earth hanging in the distant sky, would embody centuries of exploration, curiosity, and courage. Mars represents not only a scientific goal but a spiritual one, the drive to reach beyond the known, to plant life where there is none, to turn an alien world into a reflection of our persistence. It is, perhaps, the inevitable next step for a species that has always looked toward the horizon and wondered what lies beyond. Before a single human has set foot on Mars, robots have already made it their domain. They are the scouts, the silent pioneers that have crossed the void of space to roll, dig, and fly upon the red planet's surface. For decades, these mechanical explorers have sent back images and data that have transformed Mars from a distant, mysterious point of light into a world of valleys, dunes, and ancient riverbeds. Their journeys have redefined how humanity sees not only another planet but also its own capacity to reach across space with intelligence and precision. The story began with a few daring attempts in the 1960s and 1970s, when space exploration was still young and uncertain. NASA's Mariner missions were the first to fly by and later orbit Mars, capturing the first close-up images of its cratered surface. Then came the Viking landers in 1976, the first successful missions to touch down and operate on the planet. Viking 1 and 2 not only photographed the dusty landscape in unprecedented detail but also conducted the first experiments to search for signs of life. Though they found no definitive evidence, they opened the door to questions that would guide every mission that followed. For the first time, Mars was not an abstract world in telescopes, but a tangible place, with horizons, rocks, and shadows. In the decades that followed, Mars became a proving ground for robotic endurance and ingenuity. The Mars Pathfinder mission of 1997 carried a small rover named Sojourner, the first of its kind to move across another planet's surface. Barely the size of a microwave, it explored its surroundings with cautious precision, analyzing rocks and soil while sending back a stream of color images that captivated the world. That modest beginning led to greater ambitions. In 2004, NASA's twin rovers, Spirit and Opportunity, landed on opposite sides of the planet. Designed to last 90 days, they operated for years, Spirit until 2010 and Opportunity until 2018, traversing kilometers of rugged terrain, uncovering mineral traces that proved Mars once had liquid water. Their longevity and persistence became legendary, their mechanical resilience mirroring the Curiosity that built them. Then came Curiosity in 2012, a rover the size of a car, equipped with laboratories, drills, and cameras that could analyze the planet's geology in intricate detail. It landed in Gale Crater and began studying the layers of rock that tell the story of Mars's ancient past. Curiosity's discoveries confirmed that the planet once had conditions suitable for life: liquid water, essential elements, and a stable environment. Almost a decade later, in 2021, Perseverance touched down in Jezero Crater, carrying even more advanced instruments and a new companion, Ingenuity, the first helicopter ever to fly on another world. With delicate rotors spinning in the thin Martian air, Ingenuity rose from the ground, proving that flight beyond Earth was possible. What began as a brief technology test became a series of dozens of flights, scouting ahead for perseverance and expanding the boundaries of robotic exploration. These robots have done more than take pictures and samples. They have built a continuous human presence on Mars without the need for a single living body. They have watched the Martian seasons change, measured radiation, tasted the dust, and recorded the sigh of thin winds against metal. Through them, we have learned how to navigate a planet where temperatures plunge below -100 degrees Celsius, where communication signals take minutes to travel, and where every command must be planned with patience and precision. They are our eyes, our hands, our sense of touch in a world we cannot yet reach directly. Each new mission builds upon the last, shaping the path for eventual human arrival. The data collected by these machines will guide the choice of landing sites, the search for resources, and the construction of habitats. In that sense, the robots are not just explorers, they are architects of the future. They have already mapped the terrain for those who will come after, leaving their tracks etched in the dust as the first human footprints of a kind. When humans finally walk on Mars, they will be following the paths of spirit, opportunity, curiosity, and perseverance. The quiet trailblazers that turned an unreachable dream into a world known, measured, and waiting. From afar, Mars looks like a world of endless red, a dusty planet cloaked in rusty tones that earned it the name of the Red Planet. But beneath that familiar hue lies a surprisingly colorful landscape, one far richer and more varied than the first glance suggests. The reddish color that dominates its surface comes from iron minerals in the soil, oxidized over billions of years into fine rust-like dust that coats nearly everything. Yet this is only the surface layer, a thin blanket hiding a palette of browns, yellows, blacks, grays, and even blues and greens, all shaped by different minerals and geological histories. Mars is not just red. It is a planet painted by the forces of wind, water, and time. The rusty dust that gives Mars its signature color is made mostly of iron oxide, the same compound that forms when metal rusts on Earth. When ancient volcanic rocks broke down through chemical reactions with small amounts of water vapor or frost, their iron content transformed into this reddish powder. Over ages, dust storms swept across the planet, spreading it evenly and tinting the surface with its warm hue. But where that dust has blown away or mixed with other materials, Mars reveals its hidden diversity. Beneath the red lies dark basaltic rock, born from ancient lava flows that once poured from massive volcanoes. These rocks are rich in iron and magnesium, giving them a deep gray or black color that contrasts sharply with the surrounding soil. In some regions, the landscape glows with shades of yellow and gold, where sulfur minerals and oxidized salts are concentrated. Elsewhere, in ancient crater basins and dried riverbeds, patches of greenish or bluish rock hint at the presence of minerals like olivine, serpentine, and pyroxene, remnants of the planet's volcanic and watery past. Clays, formed long ago when water interacted with volcanic rock, often appear in subtle tones of gray, blue, or even pale green. To the human eye, these colors might appear muted under the thin, dusty atmosphere. But in the raw data captured by orbiters and rovers, the spectrum of Mars emerges vividly, revealing a world that is anything but monotone. The variety of colors on Mars is more than an aesthetic detail. It tells the story of its complex history. Each hue corresponds to a different process: oxidation, erosion, volcanic activity, or the action of water. The red plains speak of dry ages, when iron dust settled across the land. The dark basalt flows mark eruptions that shaped the planet's surface. The green and blue minerals whisper of a time when water seeped through the crust, altering the rock and leaving behind chemical fingerprints of a wetter world. Even the bright white caps at the poles, made of frozen carbon dioxide and water ice, add to this planetary canvas, shining like beacons at the edge of a dusty world. When the sun sets on Mars, the colors shift subtly. The light scatters through its dusty air, bathing the landscape in soft gold and pink tones. Shadows stretch long across the plains, revealing layers of texture and color that lie hidden in the harsh midday glare. In such light, the planet seems to breathe, its colors deepening and blending like the brushstrokes of an ancient painting slowly fading in and out of view. For scientists, these colors are clues, but for the imagination, they are something more. They remind us that even in a place as desolate as Mars, there is beauty born of complexity, the interplay of chemistry, geology, and time. The planet may appear red from Earth, but up close, it tells a richer story, one of diversity, transformation, and the quiet artistry of nature working over eons. Mars' reddish soil, rather than defining it, conceals its true nature, a world of hidden hues, where every stone and valley carries a shade of the planet's long and restless history. The sky of Mars is not the deep blue expanse that graces Earth, but a soft, muted hue of pink and butterscotch, a sky painted in the colors of dust and distance. When the sun rises over the Martian horizon, its light seeps through a thin, powdery atmosphere filled with fine particles of iron-rich dust, scattering sunlight in a way that turns the heavens into a quiet tapestry of warm tones. It is a sky both alien and strangely gentle, a reflection of the planet itself, cold and barren, yet glowing faintly with the residue of its iron heart. The reddish tint of the Martian sky is born from its dust. Unlike Earth, whose blue sky is shaped by the scattering of light through a dense atmosphere rich in nitrogen and oxygen, Mars possesses only a thin veil of carbon dioxide gas. Suspended within it are countless microscopic grains of dust, particles so fine they cling to the air for weeks, even months. These grains, rich in oxidized iron, are what give the Martian soil its ruddy hue and the sky its dusky glow. When sunlight passes through this haze, the shorter blue wavelengths are scattered away, while the red and yellow tones dominate, bathing the planet in a perpetual sunset light. To stand on Mars and look upward would be to see a world frozen in twilight. During the day, the sky takes on a butterscotch or salmon color, the sun appearing smaller and whiter than it does on Earth, a distant coin of light in a vast pastel dome. As evening approaches, the colors shift in unexpected ways. Around the setting sun, the sky glows blue, a faint, ethereal halo that contrasts against the rose-colored backdrop. It is one of the strangest and most beautiful phenomena of Mars, a reversal of Earth's pattern. Here, where the days are rust red, the sunsets are sapphire. This happens because the fine Martian dust scatters blue light more efficiently when sunlight must travel through the thickest part of the atmosphere at dawn or dusk. The result is a pale blue aureole at the sun's edge, surrounded by rings of pink and orange dust, fading into the dimming horizon. The thin air of Mars means the light there behaves differently from what we know. Shadows are sharper, the contrast between brightness and darkness more extreme. The sun's warmth feels weak, though it floods the land with color. Every particle of dust, every mote suspended in the air, plays its part in the planet's quiet symphony of light. The sky does not change much from place to place, for the same iron dust travels across the entire planet, carried by immense winds that sweep through valleys and across plains. During global dust storms, which can last for weeks and envelop the entire world, the sky deepens into a burnt orange haze, dimming the sun until it appears as a faint disk struggling to pierce through the gloom. In those times, the Martian day takes on an eerie stillness, as if the planet itself is holding its breath beneath its own shroud. Yet there is beauty in that stillness. The pink sky of Mars, tinged with the light of a distant sun, reminds us how fragile and varied the cosmos can be. The colors there are not just optical illusions but stories written in dust, stories of erosion, of ancient winds, of a planet slowly sculpted by time and light. For the rovers that wander across its deserts, curiosity, perseverance, and those that came before, the soft butterscotch sky is a constant presence, their only witness in an otherwise empty world. Each photograph sent back to Earth captures not just a new landscape, but an atmosphere so unlike our own that it stirs both wonder and longing. The Martian sky is a paradox, alien yet familiar, barren yet beautiful. It is a reminder that even in the silence of a dead world, there can still be color, light, and the quiet persistence of beauty in the face of desolation. Mars, though cold and still today, was once a planet of fire. Its surface bears the vast, silent forms of volcanoes so large they defy imagination. Mountains that rise higher than any peak on Earth and stretch across hundreds of kilometers of barren plain. These are the monuments of a world that once seethed with heat beneath its crust, where molten rock welled up through fractures and fissures, piling higher and higher until the planet itself seemed to breathe through stone. The great volcanoes of Mars are extinct now, their vents long cooled, their slopes dusted with the fine red powder of centuries. Yet in their colossal scale, they preserve the story of Mars's fiery past, a time when the planet's heart still pulsed with energy. The most famous of these giants is Olympus Mons, a mountain so vast that it almost seems unreal. It rises nearly 22 kilometers above the surrounding plains, 3 times the height of Mount Everest, and spans about 600 kilometers across, large enough to cover the entire state of Arizona or the country of France. From its base, the slope is gentle, barely more than a few degrees, so broad that an observer standing on its flank would see the curve of the planet before seeing the summit. Olympus Mons is a shield volcano, built by countless layers of lava that once flowed slowly over the surface, spreading far and wide like melted wax. Eruption after eruption over millions of years created this monumental dome, each outpouring of lava adding to its bulk until it became the largest volcano known in the solar system. But Olympus Mons is not alone. To its east lies the Tharsis region, a vast volcanic plateau that bulges outward from Mars's crust like an ancient scar. Here stand 3 other enormous volcanoes, Ascrius Mons, Pavonis Mons, and Arsia Mons, each one towering nearly as high as the greatest mountains on Earth. They rise from the Martian surface like a line of colossal sentinels, their calderas, vast summit craters, yawning kilometers wide. Together, these volcanoes form the heart of Tharsis, a region that once might have been the most geologically active place on Mars, where molten rock surged upward and the ground cracked beneath the planet's own pressure. The existence of such immense volcanoes tells us much about the nature of Mars itself. Unlike Earth, which has shifting tectonic plates that move and recycle the crust, Mars appears to have a single, rigid shell. On Earth, volcanic hotspots drift as the plates move, forming chains of islands like Hawaii. But on Mars, the crust remained fixed above its hot spots. This allowed lava to build up in the same locations over eons, producing volcanoes of unprecedented size. The planet's lower gravity also helped. With less force pulling downward, the mountains could grow taller without collapsing under their own weight. For all their grandeur, the volcanoes of Mars have been silent for tens of millions of years, perhaps longer. The planet's interior has cooled, its once vigorous core now sluggish, its mantle no longer feeding the fiery fountains that shaped its youth. Yet evidence suggests that the last eruptions may have occurred in the relatively recent past, perhaps as little as a few million years ago, a mere blink in geological time. If so, Mars's heart may not be entirely dead. It may still beat faintly beneath the crust, waiting for the right conditions to stir once more. To gaze upon these extinct volcanoes, even through the distant eyes of orbiters and rovers, is to glimpse the memory of a planet that was once alive in a very different way. Their slopes tell of eruptions that must have filled the thin Martian sky with ash and fire, of rivers of lava that carved glowing paths through the dark. Today, their vast shadows stretch silently across the desert plains, their calderas filled with dust, their flanks scarred by landslides. They stand as monuments not only to Mars's past but to the power of planetary creation itself. Reminders that even worlds now quiet once roared with heat, motion, and life of a different kind.